There is an old philosophical question about a tree in a forest. If it falls with nobody there to hear it, does it make a sound? If you ask a quantum physicist this question, they might say the sound was there, but you couldn't be sure the tree was, which is a strange answer if you think about it. Quantum mechanics has continuously pushed the boundaries of our understanding of the tiniest aspects of reality. Numerous experiments have revealed that particles behave like waves or can appear to be in multiple places simultaneously. In the quantum world, we can only determine the likelihood of something appearing in one place or another until we observe it, at which point it assumes a definite position. This concept troubled Albert Einstein, who once stated, "I like to think that the moon is there even if I am not looking at it." Since the discovery of the strange behavior of quantum systems, we've had to confront what appears to be an uncomfortable truth. For some reason, it seems that what we consider as reality, the location of objects and their properties, isn't fundamentally predetermined. If you don't measure or interact with your quantum system, it remains in an uncertain state. We can only describe its properties and the potential measurement outcomes in a statistical and probabilistic manner. But is this an inherent limitation of nature, where there's an innate unpredictability until a measurement or quantum interaction takes place? Or could there be a hidden reality beneath what we observe that is entirely predictable, comprehensible, and deterministic? Reality is a complicated thing, especially when it comes to quantum phenomena. Let's start with the most famous example of quantum indeterminism, the Heisenberg uncertainty principle. In the classical everyday world, there is no issue with measurement. You can take any object you like, whether it's a jet, a car, a tennis ball, a pebble, or even a speck of dust, and not only measure any of its properties as you wish, but based on the known laws of physics, we can predict those properties far into the future. All the equations formulated by Newton, Einstein, and Maxwell are entirely deterministic. If you provide the positions and motions of every particle in your system or the entire universe, scientists can accurately tell you where they will be and how they will move at any future moment. The only uncertainties we encounter are due to the limitations of the measurement tools we employ. However, in the realm of quantum physics, this is no longer the case. There exists an intrinsic uncertainty in how precisely you can simultaneously determine a wide range of properties. If you attempt to measure, for instance, the position and momentum of a particle, the energy and lifetime of a particle, the spin in two perpendicular directions, the angular position and angular momentum of a particle, you will discover that there is a limit to how accurately you can know both of these properties at the same time. The product of these properties cannot be smaller than a fundamental value, which is proportional to Planck's constant. In fact, the instant you measure one such quantity to a very fine precision, the uncertainty in the other, complementary one, will spontaneously increase so that the product is always greater than a specific value. Traditionally, we've viewed the quantum world as inherently uncertain, and this uncertainty can't be entirely eliminated. When you precisely determine a property like the spin of a particle in one dimension, the uncertainty in perpendicular dimensions must increase without limit to comply with Heisenberg's uncertainty principle. In essence, you can't cheat the uncertainty principle. Meaningful knowledge about the actual outcome of a quantum system can only be obtained through measurements. However, there has long been an alternative concept, the idea of hidden variables. In a scenario involving hidden variables, the universe is fundamentally deterministic. Quantum entities have intrinsic properties that could, in theory, allow us to predict precisely where they would end up and the outcome of any quantum experiment in advance. The catch is that some of these governing variables are beyond our ability to measure with our current understanding of reality. If we could access and comprehend these hidden variables, we'd realize that the indeterminate behavior we observe is essentially a product of our lack of knowledge about what's truly happening. With a full understanding of these underlying variables, the quantum universe would appear far less mysterious. One of the greatest physicists of the 20th century was John Wheeler. Wheeler was thinking about this quantum weirdness, about how these quanta sometimes behave as particles and sometimes as waves, when he began to devise experiments that attempted to catch these quanta acting like waves when we expect particle-like behavior, and vice versa. Perhaps the most illustrative of these experiments is shown passing a photon through a beam splitter and into an interferometer, one with two possible configurations, open and closed. Interferometers function by directing light in two different paths and then recombining it at the end, creating an interference pattern based on the difference in the path lengths or the time it takes for light to travel through the two routes. Wheeler's curiosity led him to wonder if these photons somehow knew in advance how they should behave. He would commence the experiment in one configuration, and then, just before the photons reached the end of the experiment, he would either open or close, or not, the apparatus at the end. If the light had pre-knowledge of what it was going to do, you'd be able to catch it in the act of being a wave or a particle, even when you changed the final outcome. In the realm of the physical universe, it's crucial to remember that no matter how confident we are in our logical reasoning and the soundness of our mathematics, experimental results are the ultimate judge of reality. When we conduct experiments and attempt to derive the governing rules from them, we must arrive at a consistent framework. While there are numerous interpretations of quantum mechanics, all equally successful in describing reality, none have contradicted the predictions of the original interpretation. Preferences for one interpretation over another, which many people have for reasons not easily explained, essentially boil down to ideology. No matter how uncomfortable it may be, there's a certain level of weirdness inherent to quantum mechanics that we cannot eliminate. You might not find the idea of a fundamentally uncertain universe appealing, but the alternative interpretations, including those involving hidden variables, are in their own manner equally peculiar. When we look out at the universe today, it simultaneously tells us two stories about itself. One of those stories is written on the face of what the universe looks like today, and includes the stars and galaxies we have, how they're clustered and how they move, and what ingredients they're made of. This story has two parts. The first part is about the universe we see around us, which we understand by just looking at it. The second part is about how the universe became the way it is today. Figuring this out is a bit more complicated. We can study things far away to learn about the distant past, like when the light we see today was first produced. But to truly understand it, we have to use our scientific theories, like the laws of physics and the Big Bang Theory. When we do that, we find strong evidence that before the Big Bang, there was something called cosmic inflation. However, to make our observations match our theories, we have to accept the idea of a multiverse. That's why many physicists believe in the existence of a multiverse. In the 1920s, scientists found strong evidence that the many spirals and elliptical shapes we see in the sky are not just individual stars, but are actually whole galaxies. They also noticed that the farther a galaxy is from us, the more its light gets stretched to longer wavelengths. At first, there were different ideas about what this meant, but as more evidence came in, only one explanation remained. The entire universe was getting bigger, like how dough with raisins in it expands as it bakes. If the universe is getting bigger today, and the radiation in it is shifting to longer wavelengths and lower energy, then in the past, the universe must have been smaller, denser, more even, and hotter. When we consider that matter and radiation are part of this expanding universe, the Big Bang Theory leads to three clear predictions. There should be a vast cosmic network where galaxies grow, change, and group together more as time goes on. We should find a background of low-energy radiation that remains from the early universe when neutral atoms first formed in its hot state. The proportions of the lightest elements, like hydrogen, helium, lithium, and their different forms, should be consistent, even in areas where stars have never formed. All three of these predictions have been confirmed by observations, which is why the Big Bang Theory is the leading scientific explanation for the origin of our universe. It has outperformed all competing theories. However, it's important to note that the Big Bang Theory only describes the very early stages of our universe. It doesn't tell us why the universe had those characteristics. In physics, if you know the starting conditions of a system and the rules it follows, you can make highly accurate predictions about how it will develop far into the future, limited only by your computational abilities and the inherent uncertainties in the system. But what initial conditions did the Big Bang need to have at its beginning to give us the universe we have? It's a bit of a surprise, but what we find is that there had to be a maximum temperature that's significantly, about a factor of 1,000 at least, lower than the Planck scale, which is where the laws of physics break down. The universe had to have been born with density fluctuations of approximately the same magnitude of all scales. The expansion rate and the total matter and energy density must have balanced almost perfectly, to at least 30 significant digits. It must have been born with the same initial conditions, same temperature, density, and spectrum of fluctuations, at all locations, even causally disconnected ones. And its entropy must have been much, much lower than it is today, by a factor of trillions upon trillions. When we encounter questions about the initial conditions, which essentially means why things started the way they did, we have two choices. We can either say that it's that way because it had to be and we can't know more, or we can attempt to find a process that sets up the necessary conditions. The second approach, known as appealing to dynamics in physics, involves trying to create a mechanism that accomplishes three crucial things. It must replicate all the successful outcomes of the existing model it seeks to improve upon, in this case, the hot Big Bang. Any new idea must be consistent with the established principles. It should explain what the Big Bang theory alone cannot, which includes the initial conditions with which the universe began. Any unresolved issues within the Big Bang must be addressed by the new concept. It must make fresh predictions that differ from those of the original theory, and these predictions should lead to observable, testable, or measurable consequences. So far, the only idea that has met these three criteria is the theory of cosmic inflation, which has achieved remarkable success in all these aspects. In simple terms, inflation theory suggests that before the universe became hot, dense, and filled with matter and radiation everywhere, it was primarily influenced by an immense amount of energy that was a fundamental part of space itself. This energy could be thought of as a field, or vacuum energy. However, unlike today's dark energy, which has a very low energy density, equivalent to about 1 proton per cubic meter of space, the energy density during inflation was enormous, roughly 10 to the power of 25 times greater than the energy density of dark energy today. The way the universe expands during inflation is quite different from what we're used to. In a typical expanding universe with matter and radiation, as it grows, the number of particles remains the same, causing the density to decrease. This results in a slowing expansion over time because energy density is linked to the rate of expansion. However, in inflation, where the energy is an inherent property of space itself, the energy density remains constant, and so does the expansion rate. This leads to what we call exponential expansion. In this scenario, the universe rapidly doubles in size after a very short time, and then it doubles again, and so on. In a remarkably brief period, a tiny fraction of a second, a region that was initially smaller than the tiniest subatomic particle can expand to become larger than the entire visible universe we see today. During inflation, the universe undergoes significant stretching, and this has several important consequences, including making the observable universe appear flat, regardless of its initial curvature, expanding any initial conditions from the region where inflation began across the entire visible universe, generating tiny quantum fluctuations and spreading them across the universe, making them nearly consistent on all distance scales, but slightly smaller in magnitude on smaller scales as inflation nears its end. Converting the energy of the inflationary field into matter and radiation, but only up to a maximum temperature that's considerably below the Planck scale, yet comparable to the energy scale of inflation. Creating a spectrum of variations in density and temperature that exist on scales larger than the cosmic horizon. These variations are adiabatic, meaning they have a constant entropy, and not isothermal, which means they don't have a constant temperature throughout. These outcomes replicate the achievements of the non-inflationary hot Big Bang theory, provide a mechanism for explaining the initial conditions of the Big Bang, and make numerous new predictions that differ from a non-inflationary beginning. Since the 1990s, and continuing to the present day, scientific observations have validated the predictions of the inflationary scenario, distinguishing it from the non-inflationary hot Big Bang theory. The thing is, there's a minimum amount of inflation that must occur in order to reproduce the universe we see, and that means there are certain conditions that inflation has to satisfy in order to be successful. We can model inflation as a hill, where as long as you stay on top of the hill, you inflate. But as soon as you roll down into the valley below, inflation comes to an end and transfers its energy into matter and radiation. When studying the idea of inflation, physicists have examined various hill shapes, or what they refer to as potentials. Some of these hill shapes work for the concept of inflation, while others do not. The crucial factor for success is that the top of the inflationary hill must have a relatively flat shape. As long as the top of the hill is flat enough, inflation can work as a plausible solution for the initial conditions of our universe. But now, here's where things get interesting. Inflation, like all known fields, is inherently a quantum field. This means that many of its properties aren't precisely determined. Instead, they follow a probability distribution. The more time that passes, the more this distribution spreads out. So rather than picturing the process as rolling a point-like ball down a hill, we can think of it as rolling a quantum probability wave function down that hill. Imagine inflation as a process where you're blowing up a balloon. Initially, you have a small deflated balloon, which represents the size of our universe. As inflation proceeds, it's like continuously inflating the balloon. If it takes a short time for the balloon's size to double, you now have a balloon that's twice as large. Inflate it for the same duration again, and it becomes 4 times larger. Keep going, and it will grow to 8 times its original size. After roughly 100 of these inflations, you'd have a balloon that's expanded to a size much, much larger than when you started. Up to this point, things are a little bit clear. Now let's consider a scenario where the inflationary quantum field rolls down into a valley within a specific region. In that location, inflation comes to an end, and the energy of the field transforms into matter and radiation, and this transition leads to what we recognize as a hot Big Bang. This region might have an irregular shape, but it's crucial that enough inflation occurred within it to account for the observational accomplishments we've observed in our universe. The question that arises is, what occurs beyond the boundaries of this region? Here's the issue. If you insist on having enough inflation to explain the properties we see in our universe, then beyond the region where inflation ends, inflation will persist. When we consider the relative sizes of these regions, we discover that in order to make the regions where inflation ends consistent with our observations, the regions where it doesn't end become exponentially larger. This discrepancy becomes more pronounced as time progresses. Even if there were an infinite number of regions where inflation comes to an end, there would be a larger infinity of regions where it continues. What's more, the various regions where inflation ends, giving rise to hot Big Bangs, will all be causally disconnected from one another, separated by more regions of inflating space. In simpler terms, if we think of each hot Big Bang as occurring in a separate bubble universe, these bubbles don't interact or collide with each other. The result is an ever-increasing number of disconnected bubbles as time goes on, all separated by an eternally inflating space. This is what the multiverse is all about, and why some scientists consider it the default position. We have substantial evidence supporting the hot Big Bang theory, and indicating that the Big Bang started with certain initial conditions for which we lack a clear explanation. When we introduce an explanation for these conditions, like cosmic inflation, it leads to unique predictions. Many of these predictions align with what we observe, while others emerge as consequences of inflation. One such prediction is the existence of countless universes and distinct regions, each having its own hot Big Bang event. When you consider all of these regions together, it forms what we call a multiverse. This doesn't mean that different universes have different physical laws or fundamental constants, or that every imaginable quantum outcome occurs in some other part of the multiverse. It doesn't even confirm the actual existence of the multiverse because this is a prediction we can't confirm, validate, or disprove. However, if the theory of inflation holds and the data strongly supports it, the existence of a multiverse becomes highly likely. You might not like this concept, and you might be unhappy with how some physicists use it, but until a better and viable alternative to inflation emerges, the idea of a multiverse is firmly entrenched. Now at least you understand why it's a prominent and enduring theory. If you have an inflationary universe that's governed by quantum physics, a multiverse is unavoidable. As always, scientists are collecting as much new, compelling evidence as they can on a continuous basis to better understand the entire cosmos. It may turn out that inflation is wrong, that quantum physics is wrong, or that applying these rules the way we do has some fundamental flaw. But so far, everything adds up. Unless they've got something wrong, the multiverse might be inevitable, and the universe we inhabit is just a minuscule part of it. In the world of quantum mechanics, we encounter a certain level of weirdness that's fundamental to the nature of our universe. This weirdness is seen in the behavior of quantum particles, which can exhibit properties that change or become uncertain when measured in different ways. Moreover, when we explore the concept of the multiverse, we find that it is an inevitable consequence of our understanding of inflationary cosmology, which itself is governed by the principles of quantum physics. The idea of a multiverse may seem unconventional and challenging to grasp, but it arises from a consistent framework supported by evidence. Understanding quantum uncertainty and the multiverse can be quite puzzling when compared to our daily experiences, but they offer intriguing insights into the complex and profound nature of the universe. That's it for the video. I created playlists where you can watch my videos about reality. Check it out by clicking it on your screen. Thanks for watching.